Hi, everybody. My name is Vahid, and I'm here to solve another Leetcode question with you. Thanks for tuning in. So, the question that I picked up for today is question 236 um, from Leetcode, and we're trying to find the lowest common ancestor of a binary tree. So, given a binary tree, find the lowest common ancestor, LCA, of two given nodes in the tree. According to the definition of LCA, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. So the examples that the question has provided for us are example 1. So here in this example, we have root tree and two side trees and subsequent nodes below it. The nodes that are provided are P with value 5, so this would be this node P with value of 5, and node Q with value of 1. The output here is 3. And why is that? It's because the LCA, the lowest common ancestor of these two nodes, is going to be the actual root node, which is node 3. Now we have the second example here. It's the same tree. This time Q is different. Q is node with value of 4. It's quite down there. And the output here in this case is 5. Note that a node can be its own descendant. The other example here that is given is this tree with these two nodes, 1 and 2. So it would be node 1 and 2. Note that this is not a binary search tree because 2 is on the left side of node 1, node the value of 1. And the output here, given that P and Q is going to be these two nodes, is 1. So 1 could be one of its own descendants, and that is the LCA of these two nodes. Looking at the constraints down here, we have, let me zoom in a little bit. We have some interesting information here. The node vals are all going to be unique. So if P equal to Q is provided, we're not going to have more than one node with this value. And P and Q are not going to be the same. They're not going to be the same nodes. And they will exist in the tree. So that's another good information to have. All right, let's try to see how can we go about this. So if I try to draw the provided tree, for example, 2 and 1, let's change the color. So we're always given the root. So this is where we're always going to start. And a good thing to know with trees are the fact that a lot of the time you can actually use recursion for trees. Now, to find the solution to this question, we should consider what would be an LCA. So we can say, for example, if the root that is given to us, so we have to break it down somehow. We have to break it down to the left side and the right side and call the LCA function on them again. And we have to have a certain condition where we can stop the whole recursion. Something that we can always say is if you have, for example, reached this or this, you can, for example, say that if it's null, return null. Okay. Now, the other thing that we can deduct from here is if you are here and your left is null and your right is null, you're going to be null too. That's another important information. Now, if you are either Q or P, so this is an if Q or P, return that node. So if you're here and we have found the node Q, we're going to return Q. And this side would be null. So we're going to return Q again. But we also have found P. So in this scenario, P is the one that needs to be returned. So since we're breaking down the tree, if we find either P or Q, it doesn't matter if the other one is further down in like lower, like higher depths, we're going to return the node, the P or Q that has been found first. So if you start from here and you find P, you're going to return this, and you don't need to go further down and traverse the remainder of this subtree, because either Q is going to be here, in which case P will be the answer, or Q will be on this side, in which case we need to figure it out, like where exactly that node is going to be. Let's check the example one. So we figured this one. Let me use a different color. For example one, so we figured example two. For example one, P is 5 and Q is 1. So this is our Q. So we reach here and find that this is Q. And we also have to consider a case where either the left or the right are going to be P and Q. In this case, the answer is the node itself. Okay. Now, if the answer to the left side, the right side, is not going to be Q, it's going to be null, then P will be the answer. So that's also another important thing to consider. I think this algorithm is solid, so let's just go and write it down, and we'll figure out all the edge cases and anomalies that we might run into. All right, so if root is equal to null or equal to P, or root is equal to Q, return root. So we got that out of the way. Now we need to calculate both the left side and the right side. So left LCA is going to be the lowest common ancestor of root left, P, and Q. Right LCA is going to be the lowest common ancestor of root right, P, and Q. Now, with LCA, the left side is P, and the right side is Q, or more extra parentheses here. This is Q, and this is P. We need to return the root itself. That will be our solution. Otherwise, we're gonna need to check if one side is P, the other side is Q, and right side is Q, the other side is P. So we have already covered this situation. So if okay, so I'm gonna write this down. So this is like the situation where nothing has been found, so we're just gonna return null. But if LCA is either P or Q, and we could just say if it's not null, you want to return LCA. Otherwise, return the right LCA, and we can change this to it for both cases. And I think this looks pretty good. We're doing this the Kotlin style. I love how rigorous Kotlin is about null safety. I love it. Yeah, awesome. Let's check this out. Okay. What is it saying? Unresolved reference. Oh, sorry. These need to be val. This needs to be val as well. Let's try this again. Very good. Accepted for both of the three cases. Let's try submitting. Awesome. So we got our submission and it was accepted. Good job. Perfect. So as we all know, the great thing about recursion, it's easy to write, it's easy to understand, but usually it might not be necessarily the fastest approach. All right. So keep this in mind. Now I want to try another approach, which would be an iterative approach. Oh, before moving to that approach, let's figure out the time and memory complexity of the solution. The time complexity here would be, in worst case scenario, I would say it's going to be O of n. That would be the number of nodes that we have. And the memory complexity here, because we're using the stack, so it's still going to be O of n. Okay. All right, let's move to the other solution, to the iterative solution. Now, if I clear all of this, okay, we need to clear this part. Okay. If we want to go through this question iteratively, we need to somehow keep track of the relationship that each node has to its parent. So for example, here, for the case where Q is, let me also delete this part and this part. So if Q is 4 and P is 5, we need to get the relationship between them and their parents. So we need to figure out the relationship between all the nodes and parents. So we need to have some kind of a mapping, right? This should be a parent mapping. And in order to traverse the tree, let me bring this a little bit higher so it can be seen. In order to traverse the tree, we're probably going to need another data structure. If you want to go breadth first search, so you want to go by each row and each specific row with specific depths and link these to their parents, I would say stack would be a good solution. So you can just start with this node, put it in the stack, and as you're popping it out, you can also link them to their parents, and also link them to the parents and put them in the mapping, and also add them to the stack so they can be popped in the next round. So we can add 5 and 1 to the stack, and then pop 1, 5, add these two to the mapping, add these to the stack, pop this one, and so on and so forth. And once we get this, we can get the list of parents for both Q and P. So if we do that, list of parents for P would be 3. And for 4, it would be 2, 5, 3. So we'll have to iterate these, either one of these two. And as soon as we find one node that exists in the list of nodes for the other one, then that would be the answer, the first one that we find. All right, let's go down and implement this. The implementation of this one would be a little bit more complicated. All right, so we need to create the mapping first. And this would be a mutable map of, actually, let me use IntelliJ for this. Perfect. All right, so this would be a mutable map of tree node to tree node. And then we also need to have a stack. I'm going to use array_dict, which comes with Kotlin, which is quite similar to the array_dict that is used in Java. This will be of array_dict of tree node. Awesome. Yeah, so then we need to actually go about root, and if it's not null, we're going to add it to the stack. And in the parents map, we're going to put this one itself. And we need to get the parent. So that would be another null. That would be a null. Okay, so for the root, the parent is actually a null. Oh, so this should be a nullable of nullable type. Now, once we covered the root, we can go over the stack and say, well, stack is not empty. Stack remove. So anything that we add will be added to the last element. So we need to remove the last one. So let's say val node is equal to stack remove last. Now, if the left side is not empty, it's a null, what we need to do is we're going to do this a very similar thing. Instead of null, we're going to use the node itself. And we're going to do this for the right side too. Okay, awesome. The next thing that we need to do now is for either P or Q, we need to create a data structure of all of their parents. Now, the question has told us that, let me bring this up, all null vals are unique here, but we're going to make this more general. So we're going to actually use a set. So what I'm going to call this is I'm going to call this p ancestors, p parents, and this would be a set. So it would be a mutable set of prenode. And while let's get the immediate ancestor. Or no, we can start with actually a temporary node that holds value of p. So we're going to say while p node is not null, p ancestor at p node. And we're going to go up. So let me show you what we're going to do here. So let's say we have rich q. You're going to add the value q itself. Okay. And then we're going to go one level up. We're going to add 2. One level up, we're going to add its parents, 5. We're going to go one level up, going to add 3. And then we're going to reach here. And it's null, so we're not going to add that anymore. And then for p, you need to add itself as well, because as the definition of the solution, a node can be its own ancestor. And then we're going to add its parent, which is 3, and then the parent of 3 is null, so that's where we're going to stop. All right. So p node would now be parents map a p node. Awesome. And we're going to do a similar loop. We'll call it q node is equal to q. And while q node is not null, no. We're going to say while p ancestors contains q node. So as long as the list of p ancestors does not contain node q, what we're going to do is we're going to do it this way. We're going to say q node is equal to parents map of q node. And then we're going to return q node. All right, I think this looks pretty good. Everything looks really nice and great here. Is there anything that we can improve? I am not too sure about this. I don't think we need to cover all the nodes. Let's say this is P and Q, and we have to traverse all of this. We might not need like to traverse anything else. Let's say we have this and this. So we don't really need to, for example, traverse this. As soon as we know that P and Q already are keys in this stack, in this mapping, we're fine. So that will probably happen sooner than stack becoming empty. But let's write it down. Contains the key. What doesn't contains the key P or and parents map contains the key Q. Yeah. So as long as the parents map has not yet added P or Q as a key, keep traversing the tree by using the stack. Let's copy this and let's put it in here. Pretty good, pretty good. And let's run this and see whether this will work for test cases that have been provided in here. Oh, we're getting time limit exceeded. Hmm. That is usually caused by these while loops not working properly, usually. Let me get back to here. Just to make sure that this is correct, as long as oh, okay, so this should have been an or. Because if we nullify this whole thing, this should have become an or. But anyways, I'm gonna use this one instead. All right, I think this should work. All right, it seems to be accepted for all three cases. Let's try submitting it. Awesome. Submission accepted. Good job, everybody. Thank you very much for following me. I'm going to be working more on similar questions from Leetcode and smash the like button and become a subscriber if you enjoyed this video. I'll see you in the next one.